In this video, we're going to talk about infinite limits. So sometimes the limit does not exist, right? We've seen this before. The limit as x approaches a of a function f of x does not exist. It might not exist for a couple of reasons. One reason is that the limit from the left and the limit from the right are different. And if the limit from the left is different than the limit from the right, then the limit itself does not exist. Another reason is that the function becomes very large or infinite as x approaches a. And we call this an infinite limit. So formally, we express an infinite limit as the limit as x goes to a, f of x equals infinity, or the limit as x goes to a of f of x is equal to negative infinity. Now, again, as usual, our machinery for limits from the left, limits from the right still holds for infinite limits. So let's look at the following example. F of x equals 1 over x minus 1 squared. As x approaches 1 from the left, we have x is a little bit less than 1. X minus 1 is going to be a very small negative number. We square it, which makes an even smaller positive number. And so x minus 1 squared is very small. 1 over a very small number is a very large number. So the limit as x goes to 1 from the left of 1 over x minus 1 squared is infinity. The same is true as x approaches 1 from the right. Again, x is a little bit bigger than 1. X minus 1 is a small positive number. X minus 1 squared is also a small positive number. 1 over that is going to be a large positive number. And the closer we get to 1, the larger that number is. And so the limit as x goes to 1 from the right is also infinity. Given the limit from the left and the right are the same, the limit as x goes to 1 of 1 over x minus 1 squared equals infinity. Now, we've already seen functions with limits that go to infinity. We call these vertical asymptotes. So if f of x equals n of x over d of x is a rational function, then if d of c is equal to 0 and n of c is not equal to 0, then the line x equals c is a vertical asymptote of our graph. If d of c equals 0 and n of c equals 0, then there may or may not be a vertical asymptote at x equals c. So we saw this back in chapter 1. Now if the line x equals c is a vertical asymptote of a rational function, then we know the limit as x goes to c from the right is equal to infinity, or the limit as x goes to c from the right is negative infinity, and the limit as x goes to c from the left is infinity or negative infinity. So we want to describe the behavior of the function f of x at 1 and negative 1 and identify all vertical asymptotes where the function is x squared plus x minus 2 over x squared minus 1. Now, again, why are those interesting? Because those points are interesting because those are the zeros or roots of the denominator. Now, the first thing we're always going to do is factor our function. And again, I can just see this. If you can't see it, quadratic formula is a great solution. Okay, so the roots of the numerator, that's going to be x plus 2 times x minus 1. Divided by x plus 1 times x minus 1. So this bottom is the difference of two squares. So this is our function. So our function is equal to x plus 2 over x plus 1, provided x is not equal to 1. Okay, now we want to think about the behavior of our function as x approaches 1 and negative 1. Well, let's do negative 1 first. So x equals negative 1. What do we see here? Well, here we have a function which is negative 1 plus 2, or just 1 in the numerator and 0 in the denominator. That is going to be a vertical asymptote. So we know we have a vertical asymptote at x equals negative 1. But let's also look at our limit. So let's look at the limit as x goes to negative 1 from the left of x plus 2 over x plus 1. The numerator is always near 1. The denominator, though, We're approaching -1 from the left, so the denominator is always negative and becoming very, very small. Finite number divided by a very, very small number is going to infinity, but this is negative, so it's negative infinity. Oops. Look at the right. Limit as x goes to -1 from the right, x plus 2 over x plus 1. Again, the numerator is very close to 1. The denominator is going to 0, but this time it's from the right, so it's positive. So that's infinity. And because these are different, we know the limit as x goes to -1, f of x does not exist. Okay, let's look at the x equals 1. This is a hole, right? There's a hole in the function, and we can look at this. If we take the limit as x goes to 1, f of x, that's the same as the limit as x goes to 1 of x plus 2 over x plus 1. We can do this step because we know we're never plugging 1 into our function. So we can divide those out. X plus 2 over x plus 1, well, this is equal to, using our properties of limits, limit x goes to 1 of x plus 2 divided by the limit x goes to 1 of x plus 1, which is 3/2. So there's no vertical asymptote, and the function is going to get closer and closer to 3/2. It's never actually going to reach 3/2. So this function has a vertical asymptote. If there's a vertical asymptote, then the limit from the left and the limit from the right must be either positive or negative infinity. So this one, x equals -1, is a vertical asymptote. X equals 1 as a whole, not a vertical asymptote because the limits are not positive or negative infinity. So the function kind of almost reaches 3/2. There's a hole when x equals 1, and then it goes away from 3/2. All right, so some exercises. Limit as x goes to -2 from the left of 2x plus 2 over x plus 2 squared. Well, the numerator, if we plug -2 in here, the numerator is finite. -4 plus 2, -2. So the numerator is always like -2. The denominator is heading towards 0. The denominator is getting closer and closer to 0, but it is, because we have this squared, always positive. We've got a negative number in the numerator, very small positive number in the denominator. The limit is negative infinity. The limit as x goes to -2 from the right. Still a negative number in the numerator, very small positive number in the denominator, negative infinity as well. The limit from the left is the same as the limit from the right, therefore the limit exists and is negative infinity. Next exercise. The limit as x goes to -2 from the left of x squared plus x minus 2 over x plus 2. Well, let's think about this one. If we put -2 into the numerator, we have 4 minus 2 is 0 divided by x plus 2. Again, it's 0 over 0. We can rewrite this because we are never plugging -2 into anything. We can factor limit x goes to -2 from the left. Factor the numerator. I can see this as x plus 2 times x minus 1 over x plus 2, which is equal to the limit x goes to -2 from the left of x minus 1. Well, that's simply -3. The limit as x goes to -2 from the right, same thing applies, -3. The limit as x goes to -2, the limit from the left, the limit from the right are the same, that's equal to -3. All right, we want to investigate the behavior of the function at all vertical asymptotes. X squared minus 2x minus 3 over x squared minus 4x plus 3. So the candidates for vertical asymptotes are when the denominator is 0. So we need to factor this function. We're going to factor both the numerator and the denominator at the same time. Again, I can see these factors, so I'm just going to use the ones that I can see. If I couldn't see them, quadratic formula. So this is x minus 3 times x plus 1, and the denominator is x minus 3 times x minus 1. So our function is actually x plus 1 over x minus 1, where x is not equal to 3. Okay, so that's our function. Okay, vertical asymptotes. Well, vertical asymptotes are where the denominator is 0. So the two candidates are x equals 3, and the other candidate is x equals 1. X equals 3, we can look at our behavior. Limit x goes to 3 from the left of f of x is equal to the limit x goes to 3 from the left, x plus 1 over x minus 1 is equal to 4 divided by 2, or 2. This is not a vertical asymptote because we know vertical asymptote, this limit from the left would be infinity, plus or minus infinity. Okay, x equals 1. Limit x goes to 1 from the left of f of x is equal to the limit x goes to 1 from the left of x plus 1 divided by x minus 1, and that is, numerator is finite, just 2. Finite, not 0. The denominator is getting closer and closer to 0. Again, it's negative, so this is negative infinity. We can see pretty quickly, same approach, the limit x goes to 1 from the right, f of x is going to be infinity, which means this is a vertical asymptote. Also, we know the limit as x goes to 1, f of x does not exist because the limit from the left and the limit from the right are different.